me show you how to be a good Bayesian. Change your predictions.
And now let's talk a bit more concretely, how do you incorporate Bayesian inference in your work, like especially so the kind of high energy density physics data you have, what advantages or limitations arise from using Bayesian techniques in your work?
Yeah, great question, and one that people ask me all the time. They're like, "Well, what's the point? Who cares about Bayesian inference? Why are you doing this?" To which I say, Bayesian inference is really the tool that you need to answer a problem like this. So at a very high level, right? You observe this data, and you need to understand the system that created it. And so this is it's an inverse problem, and so it's very difficult to just invert the data. You have to do it in a generative framework. And so right away, Bayesian inference is very well suited for that kind of thing. You don't have to do Bayesian inference. You can do forward modeling without Bayesian statistics, but it's just such a natural framework for it. And then on top of that, it allows you, what I think is probably the most powerful thing, is to include prior information in a way that you can't. So we have, historical data, for example, going back several decades to the older version. The Omega laser system's been around since the 90s. So we have a wealth of historical data that helps us understand these systems. And so that you can use that as a form of prior knowledge to sort of inform, your expectations of what's going to come out of what you're going to learn from these experiments. And so that, provides a self-consistent way to sort of include that prior knowledge that will, improve the statistical inference that you're able to make from these, because you can take a lot of measurements, but they're not, they may not have as much information as you need them to have. And so being able to impose prior knowledge is also very valuable. And then also, one thing we struggle with in our field is propagation of uncertainties, because you have very highly nonlinear systems, and sometimes you can't build a model that's able to, sort of characterize your level of uncertainty, and Bayesian inference folds that in completely self-consistently, correlations and whatnot, if you're doing Markov chain Monte Carlo. And even if you're doing something like stochastic variational inference, you can still get a much better understanding of the uncertainty in your system based on your data, which is very non-trivial for these systems. So I would say that's the big three reasons why we use Bayesian inference to analyze the data. It's because I think it just makes sense.
Yeah, I mean, preaching to the choir, but yeah, completely relate, of course. And actually, can you describe one experiment or project that you're particularly proud of, where you used Bayesian inference, what you measured, why it's significant, and what does the model look like?
Yeah, sure. Well, it's still ongoing, so it's not done. I don't know if I'm allowed to be proud of it if if it hasn't been published yet, but that's fine. So one thing that the sort of the what's become my main project at this point is making a sort of measurement of the equation of state of a billion atmosphere pressure plasma. So the equation of state is, just the relationship between pressure, temperature, and density. Basically, you think of the ideal gas law, van der Waals equation of state, maybe, to name a few. And so it's a very important material property, right? Because it says if you're at a temperature and density, what's the pressure, what's the energy density, and so forth. And so we've sort of developed the tools to do this at lower pressures fairly routinely. You can measure the temperature, density, and pressure of a planar experiment, for example. So you can get all the very high pressure, but you can't, as I said, there's a limit to how hard you can hit something with a laser. So you can't measure the equation of state beyond, 10 million atmospheres or so. And so, you have to go to a convergent geometry, but that's very difficult. And so sort of what's become my mission is making that measurement using Bayesian inference techniques and other statistical methods, machine learning and whatnot, to take this big data set, that, consists of multiple different X-ray cameras, spectrometers, all sorts of, the full kitchen sink, and analyzing that data set, this multi-messenger data set, comprehensively at the same time, and sort of in the data space as much as possible. So sort of from first principles, if you will. And so this was a really complicated system just to build, right? You have to build models of all these detectors and understand the statistics in some sense, and then do the inference, which is going to be a very high dimensional problem, requiring the very advanced sampling tools provided by PyMC and other libraries. And so what we were able to do is take that data set and throw this very complicated model at it, it's complicated, but it's simple, right? Because it's basically, you have your temperature and you have your density and your pressure, and you have a very simple but sort of complete physical picture of how they evolve in time and space. That's sort of parameterized in terms of these physical quantities, but flexible enough to be able to fit the data while encoding, our prior belief on the physics of the system. Like, for example, we think the temperature should go up and then down, right? And stuff like that. And so doing that, building this model that, treats the evolution of the system and then, propagates that forward. What X-rays does that produce? How do we observe those? What would we measure if that were the case? Bayesian inference, the likelihood of data given theta. And then we are able to sort of independently constrain the pressure, temperature, and density from the available suite of measurements. And so that gives you sort of separate measurements of what's the temperature and density and what's the pressure. And those are related by the equation of state. And so this gives you a very fancy way to measure the equation of state using these advanced statistical methods. And so we were able to do that for the first time, and that gives you sort of insight into what physics is happening, right? You can compare it to your models. You can do further inference on those conditions that you infer, and try and understand what's happening here. Is there sort of interactions that we aren't taking into account in the physics of the system? Is it just the ideal gas law? Is there something else going on? Are the photons that we're creating, producing their own pressure? It lets you ask a lot of interesting questions, and it's to my knowledge, it's the first measurement out there at these billion atmosphere pressures. And so, we're still working on putting that together for publication, but just the sheer lift of putting it together and doing it in a self-consistent way is something that I'm proud of, and has really pushed what JJ did with his single diagnostic single shot analysis to a more complete framework. And then because I took multiple shots of data, I think I've analyzed seven shots now, so that's a vast improvement for the statistics. Square root of n was so much more certain now.
Yeah. Damn, well done. Yeah, I know this is such a hard work, but very impressive. And so first practical question, because I'm always curious, what did you use to code the actual model, and to sample? Like, did you use any already existing package? Did you have to come up with your custom packages, maybe even custom sampler? How does it work? What does it look like?
So I am a big proponent of Python, doing everything in Python, which is an increasingly popular opinion, turns out. Python, when I first started, no one in my lab was using Python, which was crazy, except for JJ. It was everyone was using like MATLAB, Excel, Mathematica. Python
Excel. Damn, this is
a lot of people still use Excel. I will say, in their defense, what they're able to do with Excel is nothing short of magic. I mean,
yeah. I mean, at that level, you have to be an Excel.
They're doing everything I can do in Python. They are doing in Excel. It just looks ridiculous.
Yeah. Damn. Wow. Okay. But good choice. I completely support you, Ethan and JJ, in this endeavor. So
So we're big proponents of Python, And the sort of big knock on Python is that it's slow. But that's actually becoming less and less of an issue when you have things like, just-in-time compilation with JAX, and other things that are, automatic differentiation. All of that is sort of closing the gap between Python and these sort of machine, Fortran and C++ and whatnot. And so the ease of use is so much better that, coding in Python is really, I think, I mean, you obviously agree, is the practical choice at this stage. And so, a lot of it is pre-existing, right? There's the JAX libraries. A lot of code exists. I didn't have to recode, np.traps or anything like that. But there's a lot of very bespoke code that I had to rewrite in JAX. That's an implementation maybe doesn't exist that does exactly what I wanted to do. And so I had to do is a lot of software development. Considering I came into college or graduate school rather with basically zero Python experience, and so I had to teach myself from the ground up how to code in Python and then how to code, in JAX, and then how to develop a large scale software package. It's not beautiful, but it does work. And that's that. I mean, that's another thing that I guess I should add that I'm proud of is, the sheer amount of code that I've written for this project. It's a massive repository, just to, analyze a couple pieces of data. But yeah, shout out to Python, shout out to JAX. We used to use PyMC as our sampling library to do the inference. We switched recently to NumPyro because that was, this is when, NumPyro was sort of new and JAX was sort of cutting edge. And now I think PyMC uses JAX at its back end.
Yeah, I mean,
And so,
you can. Like
yeah.
Yeah, we have the three backends. So C is the default one. You can use NumPy and you can use JAX. So yeah, depending on the project you're working on, can be useful to use NumPy, or it will be faster using JAX. It depends on your model. So yeah, yeah, that's great. So yeah, but anyway, you're using a very good open source package, and you build on top of it. And you're using, it seems, what are you using as a sampler? Like latest MCMC or?
So yeah, it depends. Usually we'll use, nuts, no U-turn sampler. Do it just, I mean, you have to sort of coax it to do what you want on occasion, but it's sort of the Ferrari of samplers as far as we're concerned. Occasionally it will, when you drive a Ferrari on a road full of potholes, you will occasionally encounter a negative result. And so we may have to use, something like sequential Monte Carlo SMC or some other more robust but slower nested sampling is another one that I've used a lot. So it's unfortunate because you'd like there to be one sampler that always works, but that is never the case, and you always have to do something else. And sometimes when you get really desperate, you'll be like, all right, we got to use a different, totally different sampling library to get what we want. But that's part of the art of it and part of the fun.
It's already working for most of the, like for 98% of the cases, MCMC will be amazing. I mean, and so, yeah. And that's great to hear that you didn't have to code your custom sampler, right? So you see, folks, you don't need to write your custom samplers anymore. Like especially, I'm speaking to the among econometricians among us. Like, don't stop writing your own custom GIF sampler. Just use the ones that are in PyMC or NumPyro or Stan or whatever you're using as a probabilistic programming language. It's going to work well. And there are now more than the net sampler. There are many more of them. So
100% agree. Yeah. And I've been trying to proselytize a little bit, around at different research groups. I've got some Bayesian inference outreach presentations that I've been giving, trying to spread the word that hey, Bayesian inference is not as hard as it used to be. In the olden days, you don't have to write your own sampler. You can just use one of these excellent pre-made ones that are, I mean, they're only getting better and more sophisticated.
Yeah,
And so
exactly. So
the barrier
and
to entry is so much lower now.
exactly, yeah, it's way lower. So like now you can spin up a Bayesian model and sample from it very fast, and don't even have to worry about the sampling issues because it's all taken care of for you. So I would say it's a great time to leave.
hmm And a lot of people are scared of Bayesian inference because it sounds fancy, but it's really quite easy. You build your model, turn the crank, Bayes rule, and get out your posterior.
Yeah,
It's
yeah, exactly. Yeah, not a lot of things to do now. It's pretty much all
so
automated. So
it's solved. Yeah, Bayesian
Mm-hmm.
inference is it's all done.
Mm-hmm. Mm-hmm. Yeah. And actually, do you have any good practices that you want to share with people when they're working with big code bases, as you are? Well, in your case in Python, but can be anything else. Like, what are the good practices you've found to not lose yourself, basically, when working on these big code bases, and also probably to help collaboration, as we were talking
Mm-hmm.
about.
Yeah. Well, the first thing is always comment your code.
Yeah.
And I say this with full knowledge that I am not very good at this, but always, for your future self, at the very least, write down your thought process so you can come back to it. But then on a sort of more sophisticated level, um, there's a sort of white paper by Andrew Gell-Mann. I think it's called A Principled Bayesian Workflow, that sort of lays out best practices for constructing a model. And so, you construct your model, you test the prior predictive distribution. You say, okay, is my prior correct? And then you go. And I think one thing that's really useful, especially in the sort of work that I do, is building a sort of synthetic experiment, and making sure that you can get out the information you think you can get out, right? Because if you build this whole set of synthetic diagnostics and your model, and then you take the data and then you try to analyze it, and you actually don't get any information out, well, great. You wasted a bunch of time and money on that experiment, and you didn't get what you wanted out. And so being able to sort of, before you've even done the experiment, predict what you're going to measure, and then what information you can get out of that is hugely helpful, and really, should be a prerequisite for doing, any of these experiments, is showing that you think it's going to work. I mean, there's value in just shooting a laser and seeing what happens, but at this stage, the field is advanced enough that we should be doing this a little more predictively. And then to sort of benchmarking and testing your model along the way. And so one thing that I really struggled with is I sort of put the model together all at once, and then I just pressed go and it didn't work. And I was like, well, what? Why didn't it work? What's breaking? And so then I was like, well, okay. I took it apart, and piece by piece, and I tested each module, made sure it did what I thought it was doing, ran the inference, ran the synthetic experiment. But let's say there's no noise. It's a perfect measurement. Does this work? And so building confidence in your model is very important, and convincing yourself that it works so that you can convince others. And that helps you find a lot of the issues, because you definitely can lose yourself in the model building process. As fun as it is, once the model gets too big, there's nothing you can do. You gotta just one brick at a time, and after you place each brick, make sure that brick is a brick.
Yeah, okay. Yeah, I see what you mean.
Let me show you how to be a good Bayesian.